So, we talked about magnetism in materials, and in materials we have atoms or molecules or ions, which I am calling atoms, and each atom has several electrons, and each electron has magnetic dipole moment because of its motion around the nucleus and also because its intrinsic spin and corresponding magnetic moment. Now, it may so happen that all the electrons in an atom, they pair up in such a way that the magnetic dipole moments are cancelled in pairs, and there is no net magnetic dipole moment of the atom. Such materials in which the atoms do not have a magnetic dipole moment are diamagnetic, and we discussed how they will behave in an external magnetic field, and we found that if I put it in a non-uniform magnetic field, then it will be going from stronger field side to the weaker field side. For example, if you have a magnet here and this magnet is producing magnetic field, so that magnetic field will be like this, and of course, they will come to this side and then make closed loops inside. All those things will be there, but we are at the moment not very particular about those things, and some of them will come like that and so on. So, if the magnetic if this diamagnetic material is placed here, then it acquires a magnetic moment, and that magnetic moment acquired is in the opposite direction. This is the direction, and that we said that all right, we use our mathematical model in terms of magnetic point charges. This magnetic moment can be represented by this side, so minus qm here and plus qm here, so that the magnetic moment is from negative to positive, and use that electrostatic type of things. And we said that here the field is strong, and therefore, and this is positive magnetic charge. So, the force will be on this side, on this plus qm, the force will be in this direction, and then which will be qm times b1, right, and for this the force will be opposite, and since the magnetic field has become weaker here, so this is qm times b2, and b2 is smaller. So, the resultant will be towards right, and towards right means this magnet is repelling, the magnet is repelling a diamagnetic material, or in other words, this is stronger magnetic field, this is weaker magnetic field, and so on. So, it is going from stronger field side to the weaker field side, which is opposite the case when we put a iron nail towards close to the magnet, and it always gets attracted. So, I promised to you to show this diamagnetic effect. And water is a diamagnetic material, and therefore, water should be repelled by a magnet, and we have an experiment here where we will just try to show that yes, the magnet is repelling. So, I have this magnet here, this is a magnet, very strong magnet, and this is just some iron piece, so that it stuck here. It is easier to handle. So, I have made this handle of my magnet, and then we have other setup which we are going to show. So, first look at this test tube, and it is an empty test tube, air is there of course inside, right. So, nothing is there, and this is a thermocol piece with a hole, and this is just to hold this test tube. So, first, and this is water, this is water. So, first we will put this thing in the water and see if it floats. Yes, it floats. So, let it come to rest. First we will check that if this glass is also repelled significantly by the magnet. So, this magnet now I am bringing close to this glass, this test tube, and you watch this separation. I will go very close, and I do not see any movement in the test tube. Okay. Some air current is there. So, this magnet is not repelling the test tube to any significant, you see, any significant amount. It is very close separation, and this close separation also it is not doing anything. Okay, so now let me put water in this test tube. So, we have this syringe, and I will take some water in the syringe and put it here in the test tube. Bring this magnet from this side. I should not allow it to touch, and see, it was coming towards the magnet and towards me, and when the magnet was brought, it has started going away. It has started going away, right. Once again, from this side it is going on that side. Let me bring the magnet on this side. And see, the magnet is pushing it away, is repelling. Yes, it is repelling. Now, it is coming to this side, its velocity is towards this side, and I bring the magnet from this side without touching. Yes, it has stopped and started going away. So, you have witnessed that there are diamagnetic materials, and our very familiar water is diamagnetic, and the magnet repels. Diamagnetic material when the magnetic dipole moment of the atoms is 0, then all these things happen. What if it is not 0? If this magnetic moment m, call it m, if the dipole moment of the atoms, each atom is m, and that is not 0. So, in the material you have lot many atoms, and they will all have dipole moments, but because of the thermal motion their directions will be random. The directions will be random, and remember, the number of atoms is very, very high. Okay. So, if we take a small d tau, and I have already told you earlier what we mean by small, should not be just 5-6 atoms, right. So, at least few thousand atoms should be there, but a few thousands or few tens of thousands will also make a very tiny volume. So, if you make that tiny volume, okay, let me show it this way, because I am showing it quite spread away. So, in this tiny volume there are thousands of atoms are there. So, this is d tau. So, the magnetic moment of all these atoms taken together is again 0, and therefore, m is 0, because m was this is magnetization and this is dipole moment, right. So, the total dipole moment which is here, total dipole moment in d tau, this, and divided by d tau. So, that is magnetization, and since that total is 0, therefore, the magnetization is 0. But if you put this material in a magnetic field as we did for that diamagnetic thing, what will happen? What will happen? Suppose I put a magnetic field here, B. I put a magnetic field here like this. What will this magnetic field do? When I switch on the magnetic field, then the flux changes and the reverse current will be induced, and therefore, you will have a reverse up in opposite direction, you will have an extra magnetic moment. So, that phenomena which was there is also here. Every electron, for every electron, once you have the magnetic moment, that can be treated as a loop, and the electron is there, the charge is there, the loop is there, and magnetic field is suddenly put on. So, there will be a flux change and EMF and all those things will happen, and finally, you will have that reverse current and you will have that same phenomena here. But on top of this, each magnetic moment which is there, each magnetic moment which is there will also experience a torque, and that torque will be this m and cross b. So, and this tau is different from this tau. This is we are writing for the torque, and this was for the volume. So, remember that. So, this magnetic field will exert a torque on each of these atoms to reorient it towards this B. Remember that m cross B. If you have, if you take this any say this is the direction of the magnetic moment for particular atom, and this is B, right. So, this atom with magnetic moment in this direction can be treated as a minus qm here and a plus qm here, and because of this magnetic field you will have a force in this direction qm times b, and because of this b on this qm it will be like this, it will be like this, the force will be qm times b, maybe b1 b2, maybe b1 b2, but nevertheless there is a force from here, there is a force from here, and it will turn, and therefore all these random things are there, but then the magnetic field will exert torque and they will be oriented. The orientation will not be complete because the thermal motion is always there, collisions are always there, and the things are changing, but this condition that m was 0 will not be there, because everything will be at least partially oriented towards this direction, and therefore that will create a magnetic moment m in the direction of B. So, this is one thing, and the other thing was that reverse current induced. So, an extra magnetic moment, and when I say magnetic moment, it is same as magnetic dipole moment, will be induced opposite to the magnetic field, and this is much weaker, this phenomena is much weaker than this phenomena, and therefore total resultant you will have magnetic moment or magnetization in the direction of B. So, if the atom does not have a magnetic moment, then only this phenomena is there, and so a weak reverse opposite magnetization is induced, dipole moment is induced. And but if they do have a magnetic moment, that cancellation in pairs is not complete, maybe the number of electrons in the atom is odd, atom means atom, molecule, ion, whatever is odd, and pairing cannot be complete. In that case, there is a permanent magnetic moment, and then if you put it in B, then this magnetization which will be there, or dipole moment of those that system, it will be in the direction of B. And if it is in the direction of B, the magnet will attract. The magnet will attract. If it is in the direction of B, if this is minus qm and this is plus qm, then the direction of the magnetic moment is in the direction of B, then the force here which is towards the magnet, because this is negative charge, negative magnetic charge. So, this force is towards the magnet, this force is plus qm, so and magnetic field is in this direction. So, the force here is in the direction of magnetic field, and this is weaker and this is stronger, and therefore, it will be attracted. So, I have another test tube with another material, and let me see if I can show that in that case the magnet attracts that material, and it is not iron, nickel, cobalt type thing. So, now I have this material, this is copper sulphate in the test tube and supposedly paramagnetic. So, let us try with this. So, I will put it in this thermocol stand and try to float it here. Yes, it is floating, and then I will bring this magnet close to this test tube. Can you see that it is being attracted by the magnet? It is moving towards the magnet. See, it has changed the direction of its motion. Now, it is going towards the magnet. Now, it is going in this direction. It is, let me give it a small velocities which is visible. Okay. So, it is going, let us say, in this direction. Yeah, it is going in that direction. Now, I am bringing this magnet close, I am given a large velocity. See, it was going away from the magnet, and because of the attraction, that going away has stopped and it has started coming towards the magnet. Okay. It is coming towards the magnet. So, now it is moving in this direction, and let me give a slightly more velocity in this direction, too much, and bring the magnet from this side. So, I give a velocity in this direction, a small velocity in this direction, and bring the magnet from this side, right. So, it has started attracting and reversed the direction of the velocity. So, this is a paramagnetic material, it is being attracted by the magnet. So, this is all very nice. The experiment is showing that yes, the theory is okay. Now, among this class of materials where the atoms have magnetic dipole moment, there are few materials which have an additional feature. It is in this class only, but then there are some materials which we call ferromagnetic or anti-ferromagnetic material, where the m is very much there, this m not equal to 0. So, in this same category, but materials like iron, nickel, cobalt and some rare earths, and then lot of alloys, varieties of alloys, many alloys. So, this is a separate category among this bigger umbrella of atoms, magnetic dipole moment not being 0. Here the electrons which are overlapping between the neighboring atoms, these they interact in such a way that these neighboring moments are either parallel, or they try to align parallel to each other or anti-parallel to each other. So, in this case, in paramagnetic case, you have an atom here and this is the neighboring atom, let us say, but then there is no special effort by these atoms to make these magnetic moments parallel to each other or anti-parallel to each other. They are all randomly oriented. Because of the thermal motion, this can move in some way, this can move in other way and so on. But here you have materials which are, let us say, ferromagnetic materials. In ferromagnetic materials, what happens is, if you have an atom here and then the neighboring atom is here, and then you have electrons which are shared or which are common or which are interacting with these two same electrons interacting with both the atoms. So, the interactions is such that the atoms by themselves prefer this kind of orientation. Even if it is in some other orientation, in almost no time they will align with the neighbor, and not just one neighbor, but lots of neighbors. So, what you will have is that if this is the material, then maybe in this area you have millions and billions and trillions of atoms, all are aligned this way, Then you have another region here where they are aligned in some other way, right, in some other way, let us say this way. And at this boundary you have some reorientations. So, it will be like this. You go away and then gradually it turns. Like this, and then finally. So, this is the transition part. Here the magnetic moments, all the magnetic moments are like this. Here all the magnetic moments are like this. And here there is slight smooth transition, not very abrupt kind of transition. And this whole thing may be as large as, say, a small fraction of a millimeter, right, much more than micrometer. So, depending on which system you are talking and how it was magnetized, this size may be of that order, and you can understand that even if it is 1 micrometer cube, how many atoms will be there, and those many are all aligned, and these are called domains. You have qualitatively learned all these things in your school, that in ferromagnetic materials you have domain, and all the atoms in the same domain, they have same orientation, and that number of atoms in a domain may be billions and billions. So, like that, and this is known as the transition from one domain to other domain. That region is known domain wall. So, this is essentially a domain wall, this. Okay. So, one side of domain wall well there you have to give some margin. One side of it is this way, other side of it is this way, and so on. So you can have a domain here, you can have a domain here, and so on, like that. Okay, and these are domain walls. Here you have domain wall, here you have domain wall, like that. So even now, if you take a detour, many domains can come in that detour, right? Because you do have and you take detour that way. You take detour that way. If this whole thing is 10 centimeters, then all right, the net effect outside will not be depending on this. Still you will have magnetization equal to 0 without any magnetic field. But if you apply a magnetic field, in this kind of material, if you apply a magnetic field in this kind of material, then what will happen? That is very interesting. So suppose you have this material and you have these domains, and then you are applying magnetic field. So these are some of the domains I am showing, and the magnetic field applied is in this direction. Okay, so everywhere the magnetic field is in this direction, maybe non-uniform, but basically in this direction. Now there are some domains. Suppose there are some domains, this domain for example. Okay, so let us say this domain. In this domain, the magnetic moments are in this direction. And in this and the adjoining this domain, the magnetic fields are opposite, like this. And then this is the domain wall. So on one side it is this, other side it is this. Of course, there is some thickness where it gradually turns. But here is the domain wall. What happens? What happens? Because of this magnetic field in the domain wall, there were some transitions, smooth transitions like this, and these are oriented by this B. The magnetic moments which are close to this domain wall and which are gradually changing. So let me expand it, the domain wall little bit, and then it is now this way, it is this way, it is this way, then it is this way, and then it is this way, like this, and it turns. So these are oriented by this, and therefore what was in the domain wall will become part of the domain. Okay, what was in the domain wall, these ones, this is already oriented, but then the adjacent ones which are slightly shifted, and then slightly more shifted, then slightly more shifted, and finally come to this direction. The one which is adjacent to this, which are slightly, right, slightly this way, they will be immediately aligned with this. So what will happen? This domain wall has shifted. What was in the wall now becomes a part of this domain. So this domain has expanded, and this domain has shortened. This domain has shortened because the domain wall has shifted. So the domains in which the magnetic moments are in the direction of or close to the direction of the magnetic field, applied magnetic field, those domains expand in size, and the domains which are opposite to the magnetic field or close to opposite, they shrink, right. So the size decreases, and hence you have a large resultant magnetic moment in the direction of the field. A small field can do wonders. A small magnetic field can create such a domain wall shifting and create a magnetization which was zero, because of the random orientations of domains. But a small magnetic field can give you a large magnetization. If it is antiferromagnetic, there also you have domain. Antiferromagnetic is antiferromagnetic material. There if you have two atoms, two neighboring atoms, and then the electrons are overlapping and doing some interactions, which is named as exchange, both these named as exchange interaction. So here the exchange interaction is such that the neighboring atoms are encouraged to align their magnetic moment parallel, and here the exchange interaction is such that the neighboring atoms are encouraged to align their magnetic moments in anti-parallel direction. So if this is this, if this is this, next one will be this, next one will be this, like that. So the exchange interaction will do this. So again you have domains, if this is the material, then in the material you have such domains, and in each domain the orientation of the atoms, atomic magnetic dipole moment, will be of this kind. The neighboring magnetic moments will be opposite. Chromium is an example of that. The pure elemental chromium, the crystal structure is there, and that is antiferromagnetic. Okay, so we will stop here, and we will continue with this magnetization and magnetism in the materials. There are many things to come, and especially so called H vector.